Everyone, thanks for joining us. I welcome you all on behalf of ZB Academy for today's expert talk on Introduction to Data Science with Python by Marysia Winkels. And thank you, Marysia, for taking this session and sparing your time. About Marysia, she's a data science trainer at Go Data Driven. She completed her master's degree in artificial intelligence at the University of Amsterdam, where she specialized in machine learning. Her research was focused on a data efficient deep learning. Applying this research on medical images at a company, she kickstarted her career at the crossroads of academia and industry. So without wasting any further time, I give you the floor, Marysia. Thanks a lot. Thanks for your time.
Thank you very much. Very nice to see you all here. I want to share my screen, but the host has disabled participant screen sharing. Could you maybe make me a host so I can share my screen?
Sure. Ekta, can you help with that?
Hi, Marysia. You can share your screen now.
Okay, thank you very much. All right, you should be able to see my screen now. Hi and welcome everybody. I'm very happy to see so many of you here, and I'm very excited to be here as part of this training taster. So happy to see that so many of you have joined. Although this training taster is meant to give an insight into what a training with Go Data Driven would usually be like, our trainings are usually taught at a much smaller scale, meaning we have way more room for interactions, questions about the material, exercises, and so forth. Unfortunately, that's going to be a little bit difficult with the amount of people in this Zoom call today, but I am really interested to hear your experience with the material so far. And I'm not able to set up a poll, but I'd like to ask you to raise your hands if you have ever worked with Python before and you are a little bit experienced with Python. All right, and who of you have already worked a little bit with data analysis, or even data science? All right. All right, so before we move on to the good stuff, the actual data science, I want to tell you a little bit about me first. Already had a great introduction, of course. So I'm a data scientist. My name is Marysia, and I'm a data scientist and data science educator at Go Data Driven. Like was already said, I have an educational background in artificial intelligence and approximately 5 years of industry experience in the field of data science. However, besides actual data science work, I've always loved learning more about data science from other people's experience and perspectives, and hopefully I can offer the same to you. That's why, besides my role as a data scientist, I'm also a data science educator at Go Data Driven, where I give trainings about various data science related subjects. In addition to that, I'm also part of the organizing committee of PyData Amsterdam. We are a non-profit organization that values free and accessible programming education, for which we organize regular meetups and a yearly conference on all topics Python and data science. Unfortunately, the last year has been rather slow in terms of meetups, but we did organize a kick-ass online festival with a wide variety of talks, interviews with core contributors of open source packages like scikit-learn, and a Pandas sprint. I am doing the same at the moment for PyData Global, where we try to make this accessible for everyone around the globe and not just for people in Amsterdam. But that's enough about me. Normally, I'd also really love to hear from you what your background is, and most importantly, what you hope to gain from this training, but that's going to be a little bit hard to ask everyone who's in here. So let's instead focus on the program for today. So in this taster, I want to provide you with answers to a few questions you may have, such as, what is data science? How can it provide value? And what is the role of a data scientist? Then I want to go a little bit more in depth about what machine learning is and walk you through our first project of applying machine learning to a real data set. The course, this 2-hour session, is a taster, usually assumes some pre-existent knowledge on Python and is best suited for intermediate and self-taught Python users who wish to learn to better their practices in Pandas and visualization libraries, as well as use machine learning in Python from scratch. However, as the level of coding experience with these specific subjects may differ between participants today, and I want to keep this taster as accessible as possible, I'm going to keep it light on code, especially the pandas and visualization tools. So if you have no prior experience with Python, pandas, and simple visualizations, our Python for Data Analyst course may be better suited for you. It's great for beginners and data analysts who are mostly interested in Python as a replacement for Excel and similar tools. The Data Science with Python Foundation course does teach you more about how to create great visualizations and get the most out of your data wrangling with best pandas practices, even for the trickiest data sets. But for now and for this taster, we'll focus on the modeling side instead. So that brings us to the first question of today. What is data science? Artificial intelligence, machine learning, data science, big data, deep learning, these might all be terms that you've heard before. And artificial intelligence is the broadest term of the three. It encompasses basically every form of machine intelligence. Although we sometimes hypothetically speak of general artificial intelligence, where the AI has the ability to perform any task a human can, this is still something for the far future, and we typically only concern ourselves with narrow artificial intelligence, where machines can perform specific tasks very well, sometimes even better than humans, but are limited in scope. Machine learning is then a subset of artificial intelligence. It is simply a technique for realizing AI. The intention of machine learning is to enable machines to learn by themselves from data of the past in order to make predictions or even decisions in the future. So machine learning is any type of algorithm that learns from giving a lot of data to the algorithm. So how does this relate to deep learning or big data? Well, deep learning is simply a subset of machine learning, meaning it's also a type or collection of algorithms that learns relationships in data in order to make predictions. It might be unintuitive that this deserves a whole separate category, but if you want to know more about that, I recommend that you check out our special deep learning course or a webinar that we did for Xebia Academy Webinar Week last December. And big data? Well, we call something big data when it concerns large quantities of data, so far large, in fact, that we need separate tools to deal with them, as it's too difficult to compute manually. Much like regular data, we can use this to discover patterns and trends and make decisions, so it overlaps with machine learning in some way. But there's also the other part, extracting, storing the data, analysis of the data, visualizations, and so forth. The same can be said for data science. When we're simply concerned with the algorithms and statistics, it's machine learning. But when we're also interested in how these algorithms and statistics can bring value to the organization, when we take the time to explore the data and communicate insights from the data with stakeholders, when we bring in that domain knowledge, then it's data science. So what are some examples of data science projects? So let's say you're the owner of a movie theater and you're interested in how many people will approximately attend a specific movie in your theater at a given time slot and day of the week. You've gathered this information from the past. You have information about the amount of visitors at specific time slots. And maybe you also have some information about the movie itself that can influence prediction, the genre, for instance. It can be quite indicative, as children's movies are probably not going to attract a big crowd late in the evening. How can this prediction bring value? Well, maybe you want to use this prediction to decide whether this movie should be shown in the big or the small room, or whether to skip the showing at all, such as the children's movie night example. Another application is that of spam detection. I think we're all familiar with the junk folder from your email provider of choice, where all the unwanted emails get sent to. Using a spam detector, these unwanted emails automatically get flagged, so you only get to see the emails that you actually want to see. Another application is that of recommendations. So have you ever wondered how Netflix comes up with suggestions for what you should watch? Or where Amazon comes up with ideas for what you should buy next, and those suggestions are exactly what you need, but just never knew before? Those are also algorithms at work to recommend you the most suitable item or movie suggestion. And our last example of today is that of fraud detection. Although it might initially seem like a pretty similar example to the spam or ham example, fraud detection is actually a special case, which we call anomaly detection, because in practice, for instance, in banks, the vast majority of transactions are not fraudulent, and this makes detecting it much more difficult. But not only that, not all fraudulent transactions are clearly recognizable the same way. Maybe the fraud was committed in a different way, even though it's still. In a situation like this, we build a model of what we consider normal, and we compare a transaction to how normal it is. If it's not very normal, it gets flagged as possible fraud, and someone will probably look at it manually. All the examples that we talked about before could bring value in some way to the business, in the theater owner, the email provider, Netflix or Amazon, or the bank. That means that a regular approach of bringing a project like that to life looks like this. First, we have the ideation phase, where the business need is defined and it's assessed whether a solution could actually provide some benefit. Then we need some data. The data, like the movie theater visitors or the transaction, needs to be captured and stored. Then the model can be created. And finally, once the model has been created, software engineers, UI designers, and everyone else can get to work and implement the model to bring it to production. For instance, we can make sure that you, as a Netflix user, actually gets shown a recommendation. That means there are many people involved in this process, but the data scientist part is focused here on the middle part, the creation of the model. This is usually an iterative process where the data scientist gets some data, proceeds to clean and explore it. And based on that, they create a model and refine the results. However, sometimes in order to improve your model, you need to take a step back to an earlier step, for instance, the cleaning of the data or the pre-processing or the exploring, in order to improve it. In order to be able to do all this, a data scientist needs to have these skills. First of all, they need to be proficient with some sort of programming language. And although there are many programming languages out there, Python and R are usually the languages of choice. We have chosen to support our training with Python, as it's a great library, has a great library of resources specifically for data science available, although R is a very solid choice as well. Secondly, a data scientist needs to be able to work with the data. This means merging various data sources, filtering the data, calculating various statistics, and just generally gaining insights from the data. Unfortunately, simply plugging in the dataset you haven't explored into a machine learning algorithm and getting good results hardly ever works. It requires some understanding of the problem and the dataset in order to know what the right choices are to make. Proficiency with data visualization can really help in this case, not only for your own understanding of the data as a data scientist, but also in order to communicate findings later on. And thirdly, of course, you need some knowledge of machine learning. You need to know what the different types of machine learning are, what algorithms are out there, and what the respective advantages and disadvantages are. Your choice of algorithm is almost always based on a combination of two things. First of all, your data. What type of problem do you have at hand, such as, are you predicting a numeric value or grouping similar behavior together? And what are the limitations of your data, such as missing values or large outliers? And secondly, your goal. Selecting the right algorithm is almost always a trade-off between performance, interpretability, or explainability of your model, and the speed. Deep learning, for instance, is extremely performant in many cases, but very difficult to understand and slow to apply, while decision trees are much easier to understand, but not always as performant. And lastly, you need to know how to create your model and how to evaluate whether that model is good enough to be put into production. And these are also the skills that our training could teach you. But enough talk, let's look at an actual example, an actual use case. The use case we'll be looking at today is the Palmer penguin dataset. The Palmer penguin dataset was collected and made available by Dr. Kirsten Gorman and the Palmer Station, Antarctica. The dataset contains information about 3 separate species of penguins, chinstrap, gentoo, and Adelie. And our goal for today will be to create a model that can distinguish between these 3 types of penguins based on some body measurements. The body measurements we have are the bill length and the bill depth in millimeter, which are the measurements of the beak of the penguin, and the flipper length, which is the wing of the penguin. And finally, we also have the body mass in grams. The steps we will go through in this taster are the 3 steps that are important as a data scientist, which is data exploration, creating a model, and evaluating the model in that order. We will not go through the typical iterative process where once we have a model, we will try to improve upon that model, simply because that would take a little bit too much time for today. And there are so many things to take into account when you want to do that. Also, due to time constraints, and mostly because the prior level of experience with data exploration tools like Pandas and visualization libraries like Matplotlib, Seaborn, or Altair may differ between participants today, I will simply show you some visualizations rather than go through the code that produce all these visualizations. As I said previously, data exploration is an important part of our data science process. It aids in gaining an understanding of the type of problem that you are dealing with, which will lead you to make the right choice in algorithm to use later on, and can already give you some intuition on how feasible the problem is to solve. If we look at this chart, for example, we can see the distribution of flipper length for each of the species of penguins. On the x-axis, we have the length in millimeter in bins, while on the y-axis, we have how often these flipper lengths occur per species, where each of the species has a different color associated with it. Although there is clearly some overlap between the flipper length of the different species, it seems like it could be relatively easy to distinguish between Adelie and gentoo, the orange one, and the green one, simply based on flipper length, because Adelie seems to have a smaller flipper length in general than the gentoo. This second chart here can also tell us something interesting. We have plotted the flipper length in millimeters against the body mass in grams. And whereas we previously saw a relatively clear distinction based on flipper length between Adelie and gentoo, we now see a similar, though less prominent distinction between the body mass of these 2 species as well. But of course, our goal is beyond simple data exploration. Although we may have an intuition now on how difficult this problem is, chinstrap seems to be the problem, while Adelie and gentoo seem to be relatively easy to distinguish. We have yet to find a way to actually model this. And this is where machine learning comes in. So a definition of machine learning given by Arthur Samuel is that it is the field of study that gives computers the ability to learn without being explicitly programmed. Or by Tom M. Mitchell, a prominent machine learning researcher, a computer program is said to learn from experience E with respect to some set of tasks T, and a performance measure P if its performance at task T, as measured by P, improves with experience E. So how can we translate this to our actual example? In this case, T, the task, is to determine what species of penguins a certain penguin is. E, the experience, is the previously collected data from penguins. So the flipper length, the body mass, the bill length, and the bill depth. And P, the measure P of its performance, is the performance metric that we choose. That can be something like accuracy. So how would we model something like this? Well, one thing we could do is, for instance, use a decision tree. A decision tree is a simple algorithm that sequentially makes binary decisions in order to arrive at some conclusion. For instance, it could be that purely based on the flipper length, we can already make a distinction between the Adelie penguin and the other two. So that's what we're doing here. If the flipper length is higher than a certain value, we consider it an Adelie penguin. And if it's not, then we make a distinction based on the bill length. And then in order to distinguish between chinstrap and Gentoo, maybe we only have to look at the bill length. And we have our chinstrap, Gentoo, and Adelie. However, this is a simple example that doesn't hold for this data set necessarily. The flipper length and bill length were chosen at random, and more importantly, we have no idea what a value of X and Y would be in this case. So in order to construct our decision tree, we need to determine two things. First of all, what features to take into account. These were randomly chosen. And second, and most importantly, what threshold values like X and Y to use. Although we could, in theory, construct a tree like this manually, this would be a lot of work, especially if we have more than just a handful of examples. And that's why we present our data to a machine learning algorithm that will construct this tree for us. When we talk about data in the context of machine learning problems like this, we make a distinction between two categories. First of all, we have our feature matrix, which describes our samples. In this case, that would contain the bill length, the bill depth, the body mass, and the flipper length of every penguin that we made recordings of. And secondly, we have the thing that we want to predict, the target. And in this case, that is the specific species of penguin that corresponds with those features that we just described. So that's Gentoo, chinstrap, or Adelie. For every single penguin that body measurements were taken of, we know what species it belonged to. And our algorithm will take both of these parts, the features and the targets, and try to find a relationship between those. The idea here is that in case that you have new body measurements of a new penguin, where you don't know the target, we can use this model to predict what we think the target should be. However, we've only taken a look at the presentation just now, but what I actually want to do with you is look at this specific data set in practice in a notebook. So if I go to the next slide, there are a couple of options that you can use to get to the notebook. The notebook is located at Google Colab, where you can run the cells automatically, or you can download it from GitHub with one of these two links. Or if you prefer, you can download it from Google Colab and save the file locally if you want. I'm going to give you a minute or so to see which one you choose and get the file up here, and then I'll move on to the notebook and we'll see if we can actually make machine learning algorithm that predicts the right penguin. If maybe someone could put the link, this gdd.ly, etc., in the chat, that would make it easier for everyone involved, I think. All right, I hope you've found the notebook. I'm going to switch my screen to the notebook as well. This is the Google Colab version, and I'm going to run it locally. So here we have a IPython notebook, and in this notebook, I'll show you the code that I would use to create a model around this Palmer penguins dataset. First of all, before I do anything else, I'm going to import Seaborn and Matplotlib for visualizations, and Seaborn specifically because that's where we will retrieve the data from. About the data, we already discussed this. The data was collected by the Palmer station, and we want to use this data set to not only explore and visualize, but also demonstrate how we would do machine learning in scikit-learn with Python. Scikit-learn is a library, a package in Python that is the standard package for machine learning in Python, but also in general. It is many available machine learning models available. The API is incredibly consistent. We'll see this later on as well, which makes it really easy to simply change out a few things and have a completely different model. And it makes it really easy to apply a wide variety of machine learning algorithms. In addition to all the algorithms that are implemented, they also have a lot of handy tools implemented, which will help you out with pre-processing, module evaluation, and model selection. Scikit-learn is really the package that can help you out with almost any machine learning task that you may have, and it is incredibly easy to use. There are also other packages available that also do machine learning, but most of these will make sure that they're compatible with scikit-learn, even if they have a different focus. In this notebook, we're going to focus on the penguins datasets, and we'll demonstrate the classification of penguin species based on those bodily measurements with scikit-learn. We'll cover loading in the data through Seaborn, preparing the data for scikit-learn, because sometimes you have to make some adjustments to the dataset that you have, model creation, and immediately how to evaluate that your model is any good. And lastly, in terms of interpretability, we'll also see some model visualization. We'll start by loading in the data. And if you have this notebook or the one on Google Colab in front of you, what you can do is browse along with me and execute the cells as we go, even make small adjustments as we go. So you immediately get a feel for it, and it's not just listening to me. So loading in your data. In this case, to make it easy for everyone, we're loading the data set that is provided by the Seaborn package. Usually you'll see that you probably have your data stored either locally or online somewhere in a CSV file, and you'll want to use pandas to load it. And also scikit-learn comes with various standard data sets that can be used for practice, that can be loaded if you have scikit-learn installed on your system. But today we'll be loading our dataset from Seaborn. So we'll load the dataset, and we'll notice that as we load it, this is a pandas data frame. The dataset loaded from Seaborn will automatically be a pandas data frame and can therefore also be used as such. Pandas is a very powerful library for anything to do with data wrangling. What we do here is we load in the dataset, we assign it to our variable data, and because this is now a pandas data frame, we can explore it in the way that we normally explore pandas data frames. In this case, we choose to display the first 10 data samples in our dataset. And we notice that we have quite a few columns here. We have the species column. This is going to be our target because this is what we want to predict. We have the island, not necessarily a bodily measurement, but it is the island where the specific penguin was spotted. The bill length in millimeters, bill depth in millimeters, and flipper length in millimeters, and body mass in grams. And we have the sex. So these are the features that we have available, and this is the thing that we want to predict. But as we loaded in the first 10 data samples, you notice that all of this is actually Adelie. And it might make you wonder, do I have more data, or is all my data about the Adelie penguin? Because this is a pandas data frame, it's pretty easy to check whether we have more values in the species column, simply by referring to the variable that we assigned our data to. Between square brackets, we have as a string the name of the column that we're interested in this case, island. And we check for the unique values. So we see that even though all of these data points were spotted at the Torgerson Island, Biscoe and Dream are also islands that occur in our dataset. And we can easily do the same thing for species. And even though the first 10 species are all Adelie, we notice that we also have chinstrap and gentoo here available. However, if I take a look at this data set, there are more things that I notice. And one of the things that I notice is that besides regular values, I actually also have quite a few not numbers in here. I have a whole row of missing values here. And it seems like in the sex column, quite often my values are missing. This is a problem because if there are any missing values, we cannot give it to our algorithm in order to learn the relationship between those values and the species. For instance, this row over here, we know nothing about this penguin. The only thing we know that it was seen at Torgerson, and of course now that it is an Adelie penguin, but we know nothing else. So there's not much to learn a relationship between. So that's why in this case, we are going to have to deal with those missing values. Because if we have missing values, that means that we cannot use that information to create a machine learning model with scikit-learn. Normally, there are multiple strategies for dealing with missing data, and actually I would say more better strategies for dealing with missing data. For example, you could replace a missing value with the mean of a column. Or for example, if for a particular penguin, the value of body mass is missing, you could replace the not a number with the mean recorded body mass of all penguins. Scikit-learn provides a great interface to apply such transformations, although that is also something you can do with pandas. But for this moment, for this taster, we're going to simply ignore this and choose to discard all the incomplete data points with the pandas drop now functionality. So we create a new variable data that is simply the old data, but without any of the missing values. And if we execute this, actually, I am printing now the entire data set. We see that we have 333 rows and 7 columns. Well, before we had a lot more. Another thing we notice here is that we actually have more information than the features that we just discussed in our presentation. In our presentation, we discussed the bill length, the bill depth, flipper length, and body mass. But we also have some additional information here. First of all, we have the island. And second of all, we have the sex. Although we could incorporate this extra information, the sex of the penguin and the island where the penguin was spotted, this requires some extra pre-processing, and that's outside of the scope of this notebook. You could also even argue that maybe the sex column is not very necessary to include here because, well, it's not as, I don't know much about penguins, but I don't assume that the division between male and female is that different for the different penguin species. For this notebook, however, we're still choosing to focus on the numeric features that we have. So the bill length, bill depth, flipper length, and body mass. And that means that we are going to discard the island column and the sex column. Another thing that we need to do in order to prepare our data set to be used with scikit-learn is make that division that we talked about earlier between the feature matrix, which contains all the relevant information that you want to base your prediction on, and on the other hand, the target, the thing that you are going to want to predict. So we're going to use our knowledge of pandas to create our feature matrix X and our target vector Y. X is simply the part of the data set that only contains these 4 listed columns. And Y is the part of our data set, still every row, but only the species column. You'll notice here that the shape of our feature matrix and the shape of our target vector is what we expect. For every penguin that was spotted, we know 4 things about it. We know the bill length, bill depth, flipper length, and body mass. And we know what species it is, which is only one possible species. So we have seen in total 333 different penguins. For those, we made 4 bodily measurements recordings, and we know what species they belong to. These individual X and Y, because of how we treated it with pandas, are now also pandas data frames. Previously, with our pandas data frames, we could simply say head to give us the first 5 samples of our data set. And we'll notice that we indeed no longer have the species, island, and sex column included here, but all the other data is still the same. This is for our feature matrix X. But besides our feature matrix X, we also have our target vector Y. Our target vector Y is a vector, not a matrix, because it contains only one single value per observed penguin, which is the species that it was. Because our data was ordered and sorted, that is orderly for all the first 5 examples. Does that mean we're now ready to immediately do some machine learning? Well, yes and no. An important goal of machine learning is to create a model that doesn't only do well on the data that is already seen, but what you want to do specifically is have a model that creates good predictions on information that it hasn't seen before. For instance, if there's another researcher currently at the Palmer station, and that researcher observes the bodily measurements of a new penguin, based on those measurements, you should be able to determine, well, this is most likely a gentoo penguin, or this is most likely an Adelie penguin. But we don't know that target just yet. We want to create a model that predicts this. A model that performs well on data that it hasn't seen before is a generalized model and is a good performing model. But a problem if we don't do anything with the data set that we have at hand now and we immediately use it to do our modeling, we don't know how good our model actually is. So imagine that we have a penguin, and penguin A is a gentoo, and there are some specific measurements associated with this penguin a bill length of 33, a bill depth of 16, a flipper length of 180, and a body mass of 3,500 grams. And this specific penguin, was already present during the training of our model. That means that penguin A was an example that the algorithm used to create an understanding of what a gentoo looks like. So this is one of the data points that the model used to determine what a typical gentoo penguin looks like. If we now want to know how well our model does, asking it to classify or determine what type of penguin A is does not give us a lot of information, because it has learned what a gentoo is based on the specific example that we're now asking for. Even if the model is correct, do we really know that it has truly learned the relationship between the important features, for instance, the flipper length? Or has it simply memorized the original data points, and does it recognize penguin A from the training phase? We don't know that. And that's why with machine learning, what we usually do is we want to separate our data set into 2 separate parts. So the entire data set that we have of 333 samples, we'll split it into 2 different sets. The first one is the training set, and this is a combination of features, so the bodily measurements, and the targets, so what species it is, that will help us guide the learning process. Meaning, for instance, this is what our decision tree is going to be based on. This is what we will use as data for the decision tree to determine what features it should look at and what those threshold values should be. And then on the other hand, we keep apart the specific part of the data, the test set. That's also a combination of features and targets that we will use to evaluate how well our model has learned. So this is data, unlike penguin A, that was not used during the training phase. This is as though we created a model and we then sent someone back to the Palmer station to record all these penguins for us. It hasn't been involved in the modeling process yet. Because we make this distinction between the training set and the test set, if we train on the training set and then evaluate our model on the test set, we know for sure that it is representative of new data that will come in, because the test set has been kept separate. This is one of those functionalities that scikit-learn has also built in, besides all those models and algorithms. And in order to do this, we use the built-in train test split function that allows us to split the data in the train and the test set. This lives in scikit-learn.model selection, and we import train test split. The train test split function takes a couple of arguments. First of all, it takes the feature matrix that we have. So what kind of features, the bodily measurements, that is that X that we previously defined. And secondly, as a separate thing, it takes the targets. This is what we always have in scikit-learn. We have the features and the targets separate. Of course, these dimensions need to match. If you have 333x, then you also need 333y. Another parameter that it takes is the test size, and this is the percentage of data that will be used for the test set. The default is set to 25. We set it to 0.3 now. And another parameter that you can set is whether you want to shuffle the data or not. In this case, our data set was clearly quite sorted. All the first 10 examples were Adelie, the last 10 were all Gentoo. So we want to shuffle our data set because we want to have Adelie, Chinstrap, and Gentoo in our training set, but also have Adelie, Chinstrap, and Gentoo in our test set. So we leave that parameter alone and we accept that by default it is shuffled. The train test split function returns 4 things. For the train and the test set, it returns both the features and the targets in this specific order. So you see that first we get the features back, the train features and the test features. And secondly, we get the targets back, the train targets and the test targets. And the shapes should still match. So you see here that for our train sets, our train feature set, so our X for our train set, we have dimensions of 233 by 4. So we have 233 penguins that we have made 4 bodily measurements of. And we see that that corresponds with the target vector of our train set, our Y train that we see here. For each of those bodily measurements, we have a corresponding species of penguin that we're interested in. Then also for our test set, which is a little bit smaller because we send it to 30%, we have 100 samples for which we have 100 data points for penguins, for which we have 4 different bodily measurements, and we have 100 corresponding species. What I said before here is that the default argument is that our data will be shuffled. And in this case, that is important because our data was not shuffled before, and you don't simply want to use the first 70% as your train set and the last 30% as your test set, because then you end up in the situation where in your train set, there are only Adelie and Gentoo, and in your test set, there are only Chinstrap. And if Chinstrap was not an example in your train set, the model has not learned that this is a possible penguin species that it could predict. So it will make a lot of mistakes in that case. So it's important to shuffle your data to make sure that we have an equal division of your species in both training sets. So Adelie, Chinstrap, and Gentoo in the training set, and Adelie, Chinstrap, and Gentoo in the test set. And we can simply see if our data is in fact shuffled by calling yTest. So this will be the target vector, y, of our test set. And we'll simply check what values we have here. And it seems like, yes, in fact, this is now shuffled. I see Chinstrap, I see Gentoo, I see Adderley. I'm happy with this. So what did we do before? We started with loading in the data, in this case from Seaborn. Sometimes you'll, in your own cases, you'll also often locally load it in as a pandas data frame from a CSV file. And we've prepared the data for our machine learning model creation. What does that mean? We separated it into this X and Y, this feature matrix and target vector. We got rid of all the rows that had missing values, which is not the strategy that you would normally use to deal with your values, but it was a very simple one to demonstrate right now. Simply getting rid of all our missing values. And lastly, we made a distinction between our train set, the part of the data set that we'll be training on and tuning our model on, and on the other hand, our test set, which is what we'll use to evaluate how well our model works. That means that we're now ready to create our model and evaluate it. And again, here we'll be using scikit-learn, as scikit-learn has just a really rich collection of algorithms readily available. And depending on the case you're working on, scikit-learn most likely has a model that will suit your purposes. I've hardly ever come across a situation where the model that I needed was not implemented in scikit-learn. And no matter, of course, deciding what model you need and what model you choose, as I said before, this is dependent on your data and your goals. Your data in terms of, well, does it have any missing values or outliers that you need to deal with? What kind of data do you have? And your goals, because performance, explainability, and speed are often trade-offs. You often have to have a trade-off between those. The nice thing about scikit-learn, however, is that it doesn't really matter which algorithm you choose. The steps that you need to complete to train a model and evaluate it are pretty much the same regardless of your choice of algorithm. And the steps that you take is, first of all, well, you have to choose a model and you have to import that model. Then you have to choose your model hyperparameters by instantiating that class with your desired values. Then you train the model on the pre-processed train data by calling the fit methods. And lastly, you evaluate the model's performance using available metrics. So we're going to start with importing the chosen algorithm. And in this case, we're choosing to go with a decision tree classifier. You have to have a little bit of knowledge of scikit-learn to know where the specific algorithms live. This decision tree classifier is a type of tree model, so you can find it in scikit-learn.tree. There are other models out there that aren't all able to be imported from scikit-learn.tree. But Googling the algorithm that you're interested in will often lead you to the right part of the package as well. So we'll import the chosen algorithm. And we can quickly check the documentation around this algorithm by calling help decision tree classifier. And this will, of course, the documentation is available online as well, but this will give us the documentation associated with this decision tree classifier. And we see, if we scroll through this, that there are a lot of things that you can set when you call this class. You can set the criteria, Gini or entropy, which is a function to measure the quality of a split. You can set the splitter, the max depth, which is the maximum and the amount of depth of a tree, and many more here. And these are things that you all set before you deal with any data. So what I can do, for instance, scrolling is a little bit slow. What I can do, for instance, is see max depth. I can set the max depth over here. What will this do? It will create an instance of the class decision tree classifier with the max depth, which defaults to none, set to 1, and it will assign it to model. This is a model that we're going to train in a little bit, but at this point, we're only defining how our algorithm should work. We're not giving it any data just yet. We're just defining this is what the tree should look like. This is what it should use, for instance, as a criterion. But we haven't presented it with any data yet. So at this point, I can also show you, our model cannot make predictions on new data. If I were to ask this model, give me a prediction on these bodily measurements and what kind of penguin this is, it doesn't know yet because it hasn't seen the data before. In order to construct the decision tree associated with the data, so like the one we saw on the slides, we need to present it with our training data in terms of our features and our corresponding targets. And that's really easy to do because all we need to do is refer to the model that we just created with our decision tree classifier and call the fit method. And the fit method takes two things. First of all, what kind of data, what kind of features do I have? And secondly, what are these features associated with? So for instance, that penguin A that we just talked about, which had a bill length, a flipper length, a bill depth, and a body mass, that was an example of a Gen 2 penguin. And that's what we want to learn. So I run this and you see that's actually rather quick. The decision tree is one of those models that is really easy and quick to train. And we have now trained a model that can be used to make predictions on new data. And that new data is the data that we kept apart. So that's our test set. That's our new unseen data that we can create predictions on. And creating predictions is really just as easy as, again, referring to this model over here and using the predict method. And you'll notice that this predict method now only takes one x. It doesn't take this y test. Why not? Why are we only feeding it the features in this case? Why are we not feeding it the targets? Well, during the training phase, during the fitting phase, we want to find a relationship between the features on the one hand and the targets on the other hand. That's what we did during this fitting stage. But at this point, we have learned that relationship. And what we want to do is not learn that relationship, but we want to create a prediction on new data. And normally on new data, you don't have that. You don't have those real targets. So we can create those predictions and we assign it to a variable called ypred, so our target prediction. And we can now really easily compare these predictions against our original data to see how well our model does. Because we have our ypred and we see that for our first 10 samples, we are always predicting either Adelie or Gen 2. I don't see any chin strap in here. But in our actual Y test, the real targets that it was supposed to predict, we see that chin strap is actually one of the different penguins that was in there. So there is some overlap. We have Adelie, Gen 2, Adelie that we have here in our real targets as well. So for those, our predictions were good. And it seems like for the other ones, the predictions are also quite good. It's just that in every case that a chin strap was predicted or was the real penguin, the model was not able to recognize that and made the prediction Adelie. Of course, in this case, I'm manually comparing the predictions that I get from my model with the real targets that I have available. But I'm only comparing the first 10. And we have 100 samples in our test set. So in total, we have 100 predictions and 100 real targets. And scikit-learn also provides us with a lot of metrics that we can very easily use to compare these without having to manually do that. For instance, accuracy. Accuracy is simply the percentage of results that it got correct. So in order to use scikit-learn here, the accuracy score, we from scikit-learn .metrics, so not .tree where our decision tree classifier lived, but .metrics, we import the accuracy score. And when we call the function accuracy score, we have to present it with two things. First of all, what were our predictions? That's our ypred. And secondly, what were the real targets? What was the thing that it was supposed to predict? And if we execute this, we see that we get approximately 78%, which is pretty much what I expected based on the results that we have here. Out of these 10 results, 2 were mistakes. There were 2 chin straps that were mistakenly identified as Adelie penguins rather than chin straps. But it's pretty good. But accuracy on its own can give a little bit of a false sense of security because 78% looks quite good. I mean, you have 3 different types of penguins. If it's equally divided, you expect 33% accuracy if you just predict the same penguin all the time. So 78% is really quite nice. But there are other metrics out there as well. For example, precision and recall. So precision is the proportion of positive identifications that was actually correct. So an example here would be that you have a model that should classify email messages as spam or not spam. Precision then measures the percentage of emails flagged as spam that were correctly classified, while recall, the proportion of actual positives that was identified correctly, measures the percentage of actual spam emails that were correctly classified. So these are 2 different metrics, different from accuracy score, that measure a slightly different thing. And the reason why we have these different metrics is that depending on the problem that you're dealing with, some metrics might be more appropriate than others. For instance, in a medical context, recall is often more important because if you mistakenly tell a person with cancer that they're healthy, that is a worse mistake to make than the other way around, because it can have more severe consequences. And precision is more important, for instance, in something like a YouTube recommendation system, because you won't be able to show all the relevant videos. So it's not as important that you have identified all the relevant ones. But the most important thing is that the ones that you do show are relevant. Another one here that we have here is the F1 score, and that's a function of precision and recall that you can use when you seek a balance between precision and recall. And the reason why I'm telling you this is not only because accuracy on its own is honestly a pretty terrible measure in a lot of cases, and if you think about the problem you have at hand, you quickly get to the conclusion that for your specific problem, something else is better. But what I also want to show you is how easy it is to use a different metric rather than accuracy score with exactly the same format. In this case, we can even get a classification report which has precision, recall, F1, and accuracy of all our different classes. And the way that we do that is very similar to how we got our accuracy score. Again, in scikit-learn.metrics, we now not import accuracy score, but we import our classification report. And the way that we call our classification report, just as though it would be if we had the precision score, the recall score, is by first providing it with the predictions that we made, and secondly, with the real targets that it was supposed to identify. And when we execute this, we get a lot more information. We see that we still have that 78% accuracy that we saw before, but the scores now look a lot worse. It seems like the precision for both Adelie and Gentoo is really high, but the recall is not necessarily very high. And the worst part about this is that it seems to not be able to identify a chinstrap penguin at all. So what could we do about it? Well, I'm going to scroll back a little bit, and I'm going to scroll back to the part all the way up top where I defined my hyperparameter and I set max depth here to 1. This is a hyperparameter that is used when we're doing the decision tree learning. And by setting this to a different value, for instance, 2, we'll notice as we retrain this, that our predictions now do include chinstrap. And you'll see that not only does our accuracy increase quite a bit, but also our classification report. Simply because I made a really small change to the decision tree classifier that we were using. Maybe it's difficult to understand what this change was. But that's why I'll visualize this for you in a little bit. The important thing here is for our different possible classes, Adelie, Chinstrap, and Gentoo, we have these different metrics. We have the support, which is how many times a specific penguin class was predicted. This was previously 0. This is now 22, meaning 22 of our predictions were chinstrap. And you see that our score has gone up quite a bit as well. So I didn't actually go into when we started that when we choose algorithm, I did discuss that your choice of algorithm is determined by a lot of things, but I didn't really specify why I chose a decision tree. One of the advantages of a decision tree over some other available models is that decision trees are relatively easy to visualize. By visualizing the tree-like structure of the tree, we can understand why a model classifies samples the way it does. So let's have a look at the model that we just created. This is our visualization of our decision tree. And how do I interpret this? Well, the most important thing here is the first line. What we see happening here is that our first decision is going to be made based on the flipper length. And whenever we get a new data sample, so whenever we get a new measurement of a new penguin, we're going to have a look at what the value is for flipper length, how long their flipper is. And we're going to see if it's lower or higher than 206.5 millimeters. If it's lower or equal to, so if it's small, relatively small, then we move on to this part of the decision tree. At this part of the decision tree, we are going to compare it to the bill length. So we know that we have a relatively small flipper, and then if the bill length is also relatively small, then we're going to classify this penguin as an Adelie penguin. However, if the flipper length is lower than this value, but the bill length is actually higher than this value, we're going to say this is a chinstrap. So what you can interpret here is that the small penguin with the small flipper and the small bill length is an Adelie, and the one with a small flipper but a larger bill length is most likely a chinstrap penguin. That's what our model got from this. Then, in the other case, that our flipper length is actually higher than 206.5, we move over to this and notice that we're not actually looking at bill length now. The feature that we're looking at here is bill depth, which is a completely different feature. And we're going to compare it to the value 17.65. Again, if it's lower than that, we'll predict Gentoo. And if it's higher than that, we'll predict chinstrap. So there are two ways to get to chinstrap, both with a small flipper length and a high bill length, or with a bigger flipper length but but also a bigger build-up. So this is the model that we just created. Let's go back and see what happens when we had that bad model that would never predict the chin strap. We had that when we set the max depth to 1. So I'm going to change it. I'm going to retrain my model now, specifically with the restriction that our max depth is going to be 1. We'll see that our accuracy score decreases again to what we saw before. Our classification report is going to be worse. And we see that our model, we see why our model is making the mistakes that it does. Because we set that restriction of max depth to 1. What we were actually saying is in our decision tree, we can only ask one question in order to determine what our class is. And it decided on the question in flipper length, which means that it can only distinguish between Adelie and Gentoo. And there is no way to predict chin strap because we don't have enough questions. Our model is not complex enough to understand what was happening there. So what if we didn't set the max depth at all? Let's remove this entirely and rerun everything we did before. We see that by not restricting the depth of our tree, this is actually really becomes really difficult to read even. We get a tree that is very complicated. Remember, the only possible options are Adelie, chin strap, and Gentoo, but there are so many possible ways to get to each one that actually we notice that even though our tree has become more complicated, you may have noticed that the accuracy has gone down. Previously, we had a 98% accuracy with our simpler model that had a restriction of a max depth of 2. But because our model is now so much more complicated, it is really accurately able to describe everything that was in the train set, but at the cost of performance on our test set. What does this mean? Because our model is more complex, it actually generalizes worse and it is less performant on new data, even though it's probably going to be really good on the training data that it found. It was able to find every relationship, but it's simply remembering the data here. It's no longer able to generalize well. So in this case, our best choice was actually a max depth of 2, which we saw in the diagram before. But of course, we're not restricted to just using a decision tree. A nice thing about the decision tree is that we could simply visualize it. We could simply create the tree-like structure that we had before. But there are more models out there than just decision trees. One such example is what we call a random forest classifier. And a random forest classifier is something that really resembles a decision tree because it is still based on this principle of, well, you have a little tree and that makes a prediction. But the difference between a decision tree and a random forest classifier, it's already a little bit in the name, is that in a random forest classifier, you have a lot of small little trees. The idea of a random forest classifier is that for every time you create, you state how many trees you want to create. For instance, 100, you want to create 100 little decision trees. And every time you create a tree, you're going to create that tree on a subset of the data, a random subset of the data, and a random subset of the features. So for instance, you're going to create a tree on the first 10 samples that you have with only body mass and flipper length. That's one tree. And of course, that one tree is going to perform a lot worse than a normal decision tree on all the data with all the possible features. Of course, the normal decision tree is going to be better than this smaller tree trained on a subset of the features and a subset of the data. But you're not just going to create this one tree. You're going to create a little tree 100 times. And every time you take a different subset of the data and you take a different subset of the features. And what happens here is that even though each individual decision tree performs pretty badly, the core idea here is that the combination of all these relatively badly performing trees is going to be something that works rather well. And that's the idea of a random forest classifier. And if I wanted to create a random forest classifier, I would simply do something similar. I'll actually create a different cell here. So remember previously we said from scikit-learn.tree import decision tree classifier. If I want to use a random forest instead, I'm going to say something like from scikit-learn.ensemble import random forest classifier. So this is a different place to import it from, but it's still rather similar. And what I can now do is say help random forest classifier to give me the documentation of that I need about my random forest classifier. And we see that a lot of the things are similar to what we saw in the decision tree classifier. We still have this criterion, we still have this max depth, and there's still a couple of other ones here as well. But we now also have this extra thing, and that one is called n estimators, of which the default is 100. And that's the number of decision trees that you're going to create here. So what this means is that if we want to create a model, whereas previously we said model equals decision tree classifier, if we want to use the random forest instead, we'll say model equals random forest classifier. And we can still set max depth at 2, for instance. But we now also have this extra parameter here that we didn't have for the decision tree classifier. So that's something that we can set as well. For instance, 50. And once you've done this, what you've done is you simply changed what the model is, but all the other steps in the process can remain the same. So the steps in the scikit-learn API were choose your model and import it. Well, we've done that. That's a random forest classifier now. Secondly, initiate your model with the right parameters. Well, we did that. We changed it to n estimators and also a max depth. And then the other steps were fitting your model, which means giving it the trained data to learn from, creating predictions, and creating a classification report. But none of those things really have to do with the choice of model. So all of these steps are exactly the same. We have model.fit, xtrain, and ytrain. Nothing changed here because we were doing a random forest. We have ypred, which is the prediction of our model based on our x-test. So this is the feature matrix of our test set. Remember, you don't want to use your targets here. You're just interested in what features you have. And we can get a classification report. And we see that we actually get some slightly different results. And the interesting thing is that you can do this not only for models that resemble each other. The random forest classifier is quite similar to a decision tree in terms of the hyperparameters that it has. But there are also other models out there. For instance, from scikit-learn.neighbors, import k-neighbors classifier. A k-nearest neighbors classifier is a completely different kind of model. What a k-nearest neighbors classifier does is it simply collects all the data that you have in your training set, And whenever it encounters a new example, so for instance, a newly recorded penguin, and you want to determine what species it belongs to, what you'll do is you'll simply take the data points that are closest to it. This is the value k that we have here, the nearest neighbors, and you'll have a look at what the classifications were or what the targets were for the 5 nearest data points. So the data points that are most similar in flipper length, bill depth, and body mass. And you'll have, for instance, 5, which is the default. You'll have 5 nearest data points. And for those nearest data points, you'll make a decision, because if 4 out of 5 of those are Gen 2, your prediction is going to be Gen 2. So this is not similar to a random forest or a decision tree at all, but still we have this whole same approach of creating a model. We've imported it. We can create a model, k neighbors classifier, and let's set the number of neighbors to 8. Nothing like a tree, but this. All the other steps are still the same, and it still works. We do see that our model accuracy goes down quite a bit. There are some reasons for that. But the way that we use the API is still exactly the same. There are also other models to support vector machine or support vector classifiers. And each of these models have their own advantages and disadvantages. In this case, k nearest neighbor was not a good choice for this data set. And if you want to compare random forest to decision tree, maybe you're not only interested in the fact that the random forest in general is a more performant model, but because it creates 100 small, tiny models, it is not as easy to interpret. Sure, you could create a visualization of all the 100 tiny decision trees that were created, but it becomes less clear how the algorithm arrived at a certain decision. However, with the scikit-learn API, it is very easy to create your first model and evaluate it. Simply load in the data, make adjustments to the data so it's compatible with scikit-learn, which means getting rid of your missing values, making sure you have this distinction between X, your features, and your targets Y. And because you're doing machine learning and you want to make sure that you have something to evaluate on, create this distinction between your train set on the one hand and your test set on the other hand. And if your data is prepared, you can simply create your models by choosing your model and importing it, initializing it with the parameters that you want to try out. And what the right choices are of course, well, then you have to get deeper into what the models do exactly. But you know now that it's pretty easy to set those hyperparameters or change them around. And I have to say, scikit-learn, one of the advantages of scikit-learn is that you'll notice that there are often a lot of parameters to set, but scikit-learn will have very sensible defaults already. And then once you've created that model, you can fit it to data, create predictions, and use a metric such as a classification report or other metrics that you might be interested in to see how well your model does. And the nice thing about this is that all those other steps, fitting your data, predicting, evaluating, these all remain the same no matter what model you choose. The only thing that changes is where you import it from and what hyperparameters you are able to choose. That's simply due to the nature of the algorithm itself. So I hope that you were able to follow along with this. I want to move back to the presentation that we had here, because of course we do have limited time, and in our 2-day training we cover a lot more. So I want to briefly touch on that. Before I want to touch on that, I want to just kind of reiterate what we discussed today. We discussed what data science is and how data science is different from machine learning or big data or deep learning or artificial intelligence. And we discussed examples of data science projects. Then we talked about what the role of a data scientist is within a team we said a large part about what it means to do an AI project, what it means to do a data science project. But the role of a data scientist is really to do that modeling part. We discussed what machine learning is and what the most important concepts there are. And we saw an example of a machine learning project with scikit-learn. Before I want to tell you more about what else you could cover that has to do with machine learning and scikit-learn and data science, I actually want to finish off this session today with a Kahoot quiz that you're all welcome to join. So you should be able to see a Kahoot on the screen here, and you're all very welcome to join. You can go to the website kahoot.it or use the Kahoot app, and it will ask you for a game pin. And you can enter this number that we see here, and you should be able to join in here. And we can do a little bit of a recap of what we discussed today. I see the first person already found it. I'm going to give you some time to join here. Thanks for joining, Crazy.
Hi, Marysia. I believe you're checking the questions which are present in the Q&A forum.
Yes. I can't see them at the moment, but I'm happy to answer them.
Yes. So, people have asked a couple of questions like how one can choose which is the right algorithm for its model. The other question is, how do we treat an overfitted model? And they're also asking you to share Google Colab link. Can you see them so you can answer them?
Yes, I can see them. I can see them now. Yeah. So these are lots of interesting questions. It's unfortunate that people haven't been able to join the Colab yet. I'll definitely post that in chat later on as well. I can also briefly go back to the presentation and copy it from there. So the link is, maybe someone is able to put that into the chat.
Actually, I'm unable to copy it. That is why I couldn't. If you can just.
I'll copy it. So this should work. I'll have the screen back on the Kahoot so everyone can join. And I think this is, while everyone is joining, is maybe a good moment to answer some of the questions that I see already in here. Really lots of nice questions, but one I saw twice is how can you choose which is the right algorithm and how to assess what model you should choose for your data. Well, this is something that is really, it's quite a difficult question because it's definitely the sort of thing that you have to be familiar with the mathematics behind the different models, or maybe not necessarily the mathematics, but just the advantages and disadvantages for each of the algorithms that are out there. But like I said, in general, the things that we take into consideration is, first of all, what do you want? What is your goal with this project? Do you want something to be very interpretable? For instance, I have a background in medicine and the medical imaging. And in the medical field, when you're dealing with AI, it is really important that you're able to explain why you arrived at a certain conclusion. For instance, I know of a project where AI and data science was helping out determining whether a patient should stay in the ICU or not. And in those cases, it's very important that a model can present, we think that this person should stay in the ICU because these values, these features were over a certain value. So in those cases, decision trees, for instance, can be really helpful. Just to give a bit of context for the person who makes the eventual decision. Another reason why interpretability might be important is if you're dealing with, for instance, insurance claims. If you claimed insurance and you've been denied, you want to know what the reasoning behind that was. And in those cases, interpretability is very important. And that will mean that some of the models or some of the algorithms are no longer options because they're not very interpretable. Deep learning, for instance, is not very interpretable. It's very difficult to understand why it reached a certain decision. However, on the other hand, something like deep learning is very, very performant and very effective, especially when it concerns text or images or audio. So if you have data that is of that format, deep learning is automatically a really good choice, even though it's not very interpretable. So it's always a little bit of a trade-off, and it depends on what your specific problem is. And again, it has to do with your goal, interpretability versus performance, and the data you have. For instance, if you deal with images, that's just deep learning is so much more performance than, for instance, a decision tree, that it's almost a really obvious answer. But in order to really make the right decision, you have to know a little bit more about all the algorithms that are out there. I hope that answered the question. I'm really open to hearing more questions as well. I see there are lots of open, other interesting questions in the chat, but I also see that quite a lot of you have already joined the Kahoot. So I want to start that one first, if that's okay. See, 24 people are in here, 25 even. Nice that you could still join. And I'm going to start, and you'll see the question on my screen, and on your screen, you'll be able to answer. There'll be colors on my screen, not ABC, but just colors. And you have on your screen have to press the button that corresponds with the answer that you see here. And the first question that we get for the data science taster. Oh, it's also on time, so be sure to be quick. True or false? Machine learning is a subset of artificial intelligence. Is that blue true or red false? Okay, that's very nice, everyone. I think we have 25 people in the group though, so it's 2 people didn't answer, but everyone got this correct, so that's very nice. It was also the first question, so maybe also the easiest. The second is, what is the order of steps of data science? Data exploration, model creation, model evaluation. Is it create, evaluate, explore, evaluate, create, explore, explore, create, evaluate, or explore, evaluate, create? A little bit more diverse answers. Also, not everyone was able to participate, I think. The correct order, and I think there was actually a mistake in this quiz, because the correct answer is in fact what everyone, or most of us chose. Explore first, so your data exploration, then you create your model, and then you evaluate how well that model actually works. My apologies that the answer was incorrect. The next one, why do we use scikit-learn for machine learning? Very nice to see that the majority of you got this. The possible answers were good for data wrangling. Well, I would say that Pandas is the right library for data wrangling. Great for making interactive visualizations. Well, there are other visualization libraries out there. Includes linear algebra, ordinary differential and equation solving. That's, I think, SciPy. But scikit-learn is the one that has many available machine learning models and a very consistent API, which means that it's easy to change between the different models. 13 places up, that's very nice. The points go both on correctness and speed. What of the following will scikit-learn not allow in your training data? Continuous features, discrete values, dummy features, or missing values? Nice. Lots of people answered here. Majority got this correct. Continuous features, those are definitely allowed. We had those in our data set in our example. Discrete values, a little bit more difficult, but also allowed. Dummy features, also no problem there. But missing values is something that you have to deal with before you present your data to your machine learning algorithm. In our case, we decided to simply drop the missing values, which is, again, not an approach that I generally recommend. There are also other strategies for replacing your missing values, for instance, by the average of that column. Why do I not recommend simply dropping all the missing values? Well, that has to do with if, let's say, you start out with a data set that has 1,000 different data points, but at least 900 have some missing value somewhere. That means you're dropping 900 out of 1,000 data points, which is just a shame. You can use that data better. Why do we split our data into train and test before building the model? Nice to see. Again, most of you got this correct. In case we have any duplicates in the data, well, that really doesn't, well, that could be a problem, but that's not necessarily why we split it into a train and test set. We want our model to be scalable and easily to replicate. Well, that is definitely true, but again, that's not why we split it into a train and test set. A model can only be put into production if it passes a test. Well, a model can only be put into production if we think the model is good enough, and that is something that we have to determine ourselves. And the way to determine that is to use the test set. So the real answer here is we want to ensure that the model performs well under new circumstances. Sixth question, what's the best predictor for a model? Is that the accuracy, the precision and recall, the F1 score, or can all of these be used? Exactly. We saw all of these in our example. We saw even that the classification report reported and the accuracy and the precision and recall and F1 score per class, which means that all of these can be used. Sometimes, dependent on your problem, there is one measure that is better to measure whether it solves your problem correctly than others, but all of these can be used to determine the performance of a model. What species of penguin didn't we classify? Also very happy to see that most of you got this correct. Interesting to see that the other answer that we mostly see here is chinstrap, which was in fact not predicted correctly by the first model that we did. So I can see where the confusion maybe came from, because that first model that we created, it didn't classify the chinstrap correctly, which is in fact true. But the one that wasn't in the data set at all was the emperor penguin. And the last question, where can you go to learn more about data science and machine learning? Xivia and Go Data-Driven website, Stack Overflow, in the Go Data-Driven course, or Antarctica. Well, this is all what all of you got correct. Very happy that someone decided to answer Antarctica here, but all of these answers were considered correct. So let's have a look at the leaderboard. 7 out of 8, very nice, especially because there was one question that didn't have the correct answer available. Very nice, all of you. Well, I'm really happy that this went so well and that so many of you participated. So we have the Data Science with Python Foundation course, which is all about data exploration, which we didn't talk about that much today, mostly because it advances your knowledge of PanMass and Matplotlib and beyond. So if not everyone is at the same level, that might be wasn't ideal. We did talk about machine learning concepts, but we didn't cover everything there is to know. We didn't cover important concepts like supervised or unsupervised, or overfitting or underfitting, which I actually already saw a question about in the Q&A as well, or regularization. And of course, an important part of this course is also learn how to choose the right algorithm for your task. And lastly, there is more to scikit-learn than just what we've seen today. For instance, you may have noticed that we dropped the island in the sex column. That's because those are categorical values, but those are still things that we could include in our model. But we'd have to do more advanced pre-processing. We'd have to do pipelines and beyond. And all of this is covered in our course, or just things that you might be interested in if you want to learn more about machine learning. That was my presentation here. I see that there are many, we have some time left, so I see that there are many interesting questions here as well. Yeah, I'm ready to answer the questions. Which one shall we do first? I see a question. Is it feasible to implement the algorithms such as decision trees on your own instead of using scikit-learn? If not, why not? It is definitely feasible to implement it on your own. I mean, that's also what the contributors of scikit-learn did when they implemented their own versions of the algorithms. When I was in university and I was learning all about machine learning, what we had to do was code everything from scratch, including neural networks, including decision trees, including something like an SVM, because I think personally that's a really nice way of really learning what you're doing if you code everything from scratch. But of course, even though that is something that you can do, I would advise you to use scikit-learn instead, because it is all pre-implemented. The defaults that the parameters have are definitely very sensible. It is optimized for speed as well. So, and it's of course just easier to use an implementation of someone else when it's so easy to make your adjustments than to implement the algorithms all yourself. But it's definitely something you can do. And I actually, if you're really interested in knowing how the different models differ, I would recommend that you spend some time on that. I think it's a really nice way to learn more about it as well. So I think we've answered this question. Of course, if my answer is not sufficient, then you're very welcome to highlight it and maybe ask a new question. I think we've answered how to use the, you have the Colab link, I think, available. How do we treat an overfitted model? So this is one of the concepts that we didn't discuss in this taster, but it's a very important concept nonetheless. What happens sometimes is that the first model that you train, in our case, those were quite good. But what can happen is one of two things. One of them is underfitting, and in underfitting, your model is simply not complex enough to capture how complicated the data is. It's not good enough to capture the real world. And that can be because of the data or because of the model. And on the other hand, you have overfitting. And in overfitting, we have the problem that our model performs really well on the trained data. So it performs really well. It's very easy to to make a prediction for data points that it has already seen, but it doesn't generalize well. And what it means that it doesn't generalize well is that it's not able to provide predictions on new data samples. An example of this could be, for instance, if you want to create a model that predicts the value of a house, predicts housing prices. Let's imagine that you have very simple data, for instance, only the square footage of a house. In those cases, it would be impossible to correctly assess what the real value would be, because, for instance, something that really matters in a house price is not only the square footage, how big it is, but also the location. I imagine that the same square footage in the city center of London is going to be more expensive than the exact same amount of square footage in some remote village somewhere in the north of England. And sometimes your model is simply not complex enough. Your data is good enough, but if you basically say your price is always just going to be 2 times the square footage, that's not a complex enough model. So in those cases, you are underfitting, and your solution is either to think about the data that you have at hand and make that data more descriptive of the problem you have, or to allow your model to become a little bit more complicated. On the other hand, if you have an overfitted model, you have a model that is very accurately able to predict the house prices of the data points that were in the data set, but it's not able to generalize to new data samples. In those cases, your model is too complex. And this is something that we actually already saw in our penguin example. When we set the max depth of our decision tree to 1, our model was not complex enough, and we saw that the accuracy was only 78% because it was only able to distinguish between Adelie and Gentoo, and it wasn't able to model that some penguins were not an Adelie or a Gentoo. Sometimes it's a chin strap, so that was an underfitted model, and we could fix that by allowing the model to become a little bit more complicated, setting the max depth to a higher value. When we set that value to, well, no restriction, there was no max depth, we saw that we got a very complicated decision tree, like a very, very intricate, very complicated decision tree. And I'm sure that that very complicated and intricate decision tree was able to perfectly model the training data, but we saw that the accuracy on the test data actually went down compared to when we had a restriction on there of a max depth of 2. So in that case, it was actually overfitting, and we prevented the overfitting by making sure that the model was less complex. It only had a max depth of 2, so it was not allowed to become as big as it became. I hope that answers your question. So the question was, how do we treat an overfitted model? And my answer here is, both with underfitting and overfitting, you can take a look at the complexity of the model that you have, and in the case of underfitting, also determine whether you have enough data to actually model this problem. Are there any more questions? Anamika, maybe you can, you found some more questions? Well, in that case, if there are not any more, then I would like to thank you all for your time, and hope you managed to find the Google Colab link and learn something from today. And thank you very much for having me.
Hi, am I audible?
Yes, you are.
Yes, you are.
Oh, I'm really sorry. There must be some network issue here. So, yeah, thanks a lot, Marysia, for taking such an informative and interactive session. I'm sure most of people's query must have been resolved right now, and they would have an idea about what data science using Python is. So, the floor is still open. If somebody has a question, you can also place it in a QA forum or on the chat portal. We'll be happily addressing you all. Secondly, I would just like to inform you that keeping all these things in mind, what possible skill set is required in order to become a data scientist or let's say a machine learning engineer, we have curated two different courses. So I'm just going to quickly show my screen. Let me know if that's visible.
Yes, it's visible.
Yes, it's visible.
Yeah, so we have one course which is a certified data science with Python Foundation, and the batch starts from 31st of May. It's a 6 half-day course, and the timings would be from 5 p.m. to 9 p.m. as per, CET. The details for this course, I will be sharing the link on the chat portal. There is also discounts running. The other course which we have is Certified Data Science for Product Owners. So another the start day is from 2nd of June. It's a 4 half-day program. I will share the link for our website and all the related information on the chat portal. Kindly go through it if you are interested in learning data science with us, because keeping in mind all the industry requirements and the skill set required, we have curated both of these courses, and these are completely online live instructor led sessions. We're also running with some discounts on the price, so do check that. The number will be mentioned in the chat portal along with this email ID so that you can reach out to us if you wish to have a further discussion.